across your sites. So well, just to simplify the understanding of how MPLS IP VPNs work, we'll assume that there is only one service provider cloud, and this particular slide demonstrates how you can build connectivity across the yellow VPN sites and the green VPN sites. You can see towards the left that there are 2 yellow sites and 2 green sites. So the yellow sites belong to the same company, and then green sites belong to the same company, but they are in 2 different geographical locations. But assuming that they're taking service from one service provider, which is represented by this orange cloud, all they need to worry about is having connectivity to one of the edge routers. And it is possible that they have different kinds of routing protocols that are running in their network. They don't have to worry about making any changes to that. They could be running EBGP, OSPF, RIP, or they could be running plain static routes depending upon how big they are. And the service provider is going to build all the connectivity to all routers within his network, and he's going to take the responsibility of connecting all the yellow VPN sites on the left to the yellow VPN sites on the right, and the green VPN sites to the left to the green VPN sites on the right. And this is typically, this connectivity is provided using IBGP connections. Let's get into some more details about how these things work. So for implementing IPVPNs, when they were deciding what is the best way to go about providing this service, BGP was chosen as the routing protocol to provide this service. Now you might ask, why BGP? Because BGP is the only routing protocol that can support a large number of routes. If you are aware of routing, you know that BGP is the preferred protocol of choice for supporting the internet routing table, which is close to maybe 300,000 routes by now. But typically routers build their support for supporting up to 1 million routes or even more. So when we are talking of that kind of scale, BGP is the only routing protocol that can support such a large number of routes. One of the main reasons is that all it ensures is there is a keep alive message going between the peers, and it doesn't have to exchange all the information all the time like some of the other routing protocols do. So there is a significant reduction in the number of protocol packet exchanges. So that's why BGP is used. And another reason why you want to go with BGP is because it is very flexible in terms of supporting different kinds of protocols. All we need to do is say what type of information is being exchanged between the 2 routers, and as long as the 2 routers agree, you can exchange that information. Like for example, you can build extensions to support IPv6 routes, or in this particular case, the routes combined with a VPN for making them as VPN IPv4 routes. So it is very flexible in supporting different kinds of protocols. And a third big advantage of using the BGP as a routing protocol is that it doesn't mandate that the 2 routers which are BGP peers are directly connected. As long as there is connectivity between 2 routers, you can run BGP between them. Now this is a very big deal because it allows the VPN information not to be stored in the intermediate P routers. If you notice, the way service provider is going to build the network is that the P routers are really super fast routers, and you want to keep the load to a minimum in the P routers. You want to put all the intelligence towards the edge, and all the high-speed networking technologies would be handled by the P routers. So you don't want it to be bothered with doing a lot of layer 3, because any, as you know, route lookup is a very costly operation. Then another reason why you want to go with BGP is that it can carry any information attached to a route as an optional BGP attribute. You can define additional attributes that will be transparently forwarded by any BGP router that does not understand them. Basically, this means that BGP allows you to associate some characteristics or some colors to different routes that it carries. It's not just the routes, it is routes with some characteristics. And this can be very useful in coming up with different kinds of routing policies while distributing the routes amongst its peers. And one of the other things for implementing IPVPNs is the use of MPLS. As you know, MPLS combines the benefits of layer 2 switching with layer 3 routing and switching. It combines the benefits of the overlay model, such as the security and isolation among the customers, with the benefits of simplified routing that a peer-to-peer model brings. We also mentioned earlier in the presentation as to how MPLS is acting like a converged core. The service provider can build one network based on MPLS, and it can cater to customers running an ATM network, and frame relay network, or anything for that matter. So it's a significant cost saving. MPLS VPN provides the capability to commission IP network infrastructure that delivers private network services over a public infrastructure. So one of the prerequisites for the service provider when providing MPLS IP VPN services is that the LSPs must exist between all the endpoints before transport connection may be established. Now this is very important because that is the only way the service provider can sell a service to the customer, saying no matter where your remote offices are, we will provide connectivity. And only way you can achieve that is by having these LSPs existing between all the edge routers. Now this is not going to be a waste because you can reuse the same LSP for different kinds of traffic. It could be IP traffic, it could be L2 transport traffic. You can use the same LSP that you built. In this slide, I am using LSP and tunnels interchangeably. I think tunnel in this case really stands for the MPLS LSP that is another reason is that it becomes very scalable, which means that for different VPN customers, I could be using the same LSP for transporting the traffic. So it makes it very scalable. By scalable, we mean that the service provider gets the capability to support more and more customers with less and less of provisioning within his network. Now there are different kinds of MPLS tunnels or LSPs that you can build within your network. If you use the RSVP protocol to build, you can build traffic engineering and resource reservation based tunnels. And if you want just the best effort kind of a tunnel that you want to build, you would use the LDP protocol. This is again a service model that a service provider can choose. There are a lot of customers who will say, I want this amount of bandwidth to be guaranteed for my traffic, in which case the service provider is going to sell them the LSPs which are built based on RSVP. And then there are some customers who say, as long as I get the connectivity, it should be fine. Then they are not looking for very stringent QoS requirements, in which case they can use LDP to build the LSPs and sell that service. Now, there are some other terminologies that we need to be aware of. We are really getting into the implementation of MPLS IP VPN. So one of the terminologies that you will find people using is this called VRF. Basically, is nothing but VPN routing and forwarding information. Then route target is another terminology that people need to be aware of. It is nothing but a color or an attribute that you associate with a particular BGP route. And then there is another terminology called as route distinguisher. We talked earlier about a scenario wherein we want to be able to use the same IP address across different customers. So the route distinguisher allows you to do that. If you see the thing in blue just below, for every IP address that you learn, if you tag it with a route distinguisher, it makes a particular route unique. That means two different VPN customers can use the same IP address, but when I club it with the route distinguisher, which is unique for each customer, the whole thing becomes unique. So if you're familiar with BGP, you know that BGP has this community attribute, extended community attributes that it uses for transporting the routes from one peer to another. The route targets, as I said, they are carried as extended community attributes. And you can define import and export route targets for each particular VPN on the peer routers. We will see how this is very useful in the next slide. The peer routers that service the same VPN have the same route target configured for that VPN. This ensures that the VPN specific information remains only in those relevant peer routers. Now this is where the security comes into picture, which means the service provider is ensuring that there is no leaking of routes across the different VPNs. It can be associated with routes based on where they all lead to a specific site or QoS. Now let us see the example of how route targets can be used. Now let's look at the slide here. On the top we have a PE router which is providing service to two different VPNs, VPN A and VPN B, and they have their corresponding remote sites. At the VPN B site 2 is all the way at the bottom, and the VPN A site 2 is all the way to the right. Now let us see how we can use the route targets to ensure that there is connectivity between the sites of VPN A and then sites of VPN B. So you define all your route policies and VPN definitions at the edge router, right? And then you create all the different VPNs. And when you get updates from a particular site, then you send the BGP update by using the route targets. Whatever is configured as the export route target, you send that update with that export route target. And on the other side, you are going to configure import route targets. So only when the export route target matches the import route target, those routes are installed in the edge router. So that way you ensure that only the routes exported by VPN A with the export route target A gets installed in on the remote site wherein he is configured with to import route target A. So that way there is the service provider ensures that there is no routes of one VPN are not going to the routes of another VPN. So a typically IBGP update would look something like this, wherein you have the VPN IPv4 prefix, which is what is the main route that is being exchanged. As I said, this would be a combination of your route distinguisher plus the IP address, making it a very unique thing. And then you would have the next hop address. This is typical of any routing protocol where you capture the next hop address to where you can send the route to. Then it is going to contain the extended community attributes. It's going to contain the MPLS label. Basically, you need to be able to identify which VPN it belongs to when it reaches the other end. And then other standard BGP attributes like local preference, MED, ASPARC, and things like that. So let us look at the, when you're looking at a router which is providing IPVPN service, let us look at how the control plane looks. This is basically a zoom in inside the edge router. If you see towards the left, you have all the customer edge routers, and you have the pink customer, the green customer, and the blue customer, and they have the flexibility of choosing any routing protocol that they want, and there is a separate routing domain which is a main requirement of VPN for each of these customers. Now, if you want to exchange this VPN specific information from one provider edge router to another provider edge router, you use the multi-protocol IBGP, and for that you add the route distinguisher to each of the routes in the VRFs, and you form this big VPN IPv4 table, and this is the big routing table that gets exchanged across the edge routers, and we saw how the route targets can be used to uniquely identify each of these VPN routes. So when it goes from one BGP peer to another BGP peer, it takes these routes, and depending on the color that is associated with each of the routes, it puts them in the corresponding VPN routing tables. So in this case, when it comes, if you look at the right, when the BGP updates come to the egress edge router, it is going to put all the pink routes into pink VPN, green routes into the green VPN, and blue routes into the blue VPN. And then that in turn is going to establish connectivity with the remote PDs. So this way, all the pink VPN customers can talk to each other, all the green VPN routes can talk to each other, and all the blue VPNs can talk to each other. Now, in the middle, we have to talk about the global routing tables that are present. We need to be able to connect each of the provider routers to each other, and that is achieved through this global IPv4 routing tables, wherein you can be running your OSPF or ISS, and then you are also running your MPLS protocols to set up the tunnels. And this picture, the next slide is going to give more clarity. So you can see that the MPLS protocols and OSPF help build these tunnels between the edge routers, and each of the VRF information or the VPN information is going through these tunnels using the MPLS updates. Now, typically, how does this look when we are talking of the data plane? So previously we saw the control plane, how things are established. Now, when you actually send a packet, what is it that you do? So in this particular case, let us walk an IP packet from one customer premises to, let's say, the head office, which is CE1, to a branch office, which is CE2. Now, he sends an IP packet to PE1, and you can see below that the first process that happens is that you associate it with a particular VPN based on the interface on which you got the packet, and then you are going to encapsulate it with a VPN label, which is going to uniquely identify the customer. And then, as I said, one of the requirements is that you have an LSP built from the ingress to the egress. So from PE1 to PE2, you have an LSP that is built. So you add the second label, which is the tunnel label, to PE2. So basically, the packet gets encapsulated with two different labels. One is the VPN label identifying the customer. Second is the tunnel label identifying the egress router, and it is sent on this onto this tunnel. So it goes through the next router is P1, which is a core router. Now he's just going to look at the tunnel label and he's going to switch it to P2. If you're familiar with the MPLS concepts, there is something called as a penultimate hop hopping, which can remove the tunnel label if it is just one, if the egress is just one hop away. So that can possibly be configured, or it need not be configured. So this is up to the service provider. So once it reaches P2, the fourth process that is mentioned here, he knows that what VPN the packet represents. So he's going to strip off the VPN label and he's going to send the IP packet to CE2, because CE2 is the only guy connected to the VPN customer, which is CE1. So this is basically how the data packet flows. So we talked about this architecture in terms of the control plane, where BGP sets up all these paths, and then we talked of the data plane, wherein there's a lot of encapsulation to ensure that traffic does not go between VPNs, but it remains within the VPN. So you can see that this is quite a complex thing. So you can understand the kind of technology that is required to build these kind of routers. All the big companies are investing huge amount of money to make sure that this process is really fast. It has enough resiliency built into it. You need to have different kinds of processors to help achieve these kind of capabilities. As I said, the kind of scale that we are talking about is to be able to support millions of routes, and the resiliency is they want packets to switch in less than 50 milliseconds across. So this is a huge science in itself, and all the networking companies are trying to solve all these kind of problems. Now, let me just, in the interest of time, let me rush through some of the possible situations that VPN customers might run into. Now, it is possible that the two different VPN sites are in two different autonomous systems. Now, this functionality might be used by a VPN customer who has connections to several different service providers. Or the different connections to the same service provider but in different geographic regions, each of which could have a different autonomous system. Now, this is an interesting problem which is depicted in the next slide here. As you can see that the VPN customers are buying service from two different service providers, not just one. And basically the problem statement is still the same, that one of them is the head office, one of them is the branch office, and they want to talk as if they are on a private network. So now the service providers need to work out an agreement wherein they can build this kind of connectivity. And typically MPE BGP is used to provide this. So there is another interesting scenario wherein the customer of a VPN service provider might also be a service provider for an actual customer. He could also be a VPN service provider for another customer. So in which case, this is an interesting scenario wherein you are a carrier of carrier VPNs. So this is also possible. It depends on the kind of service provider with whom you are getting the service, and it also depends on the kind of geographical locations where your sites are. So now one of the common questions that all service provider ask of the companies are, how do I ensure that the traffic from one VPN does not affect the traffic from another VPN? There could be a storm of packets coming from one customer which might ruin the particular router. Now, for these kind of problems can be solved by a lot of configuration wherein you can control the amount of traffic coming into a particular VPN. So there are typical security related configuration that you would use in every router can be leveraged here as well. So now one of the situations that we want to consider is how to provide access to the internet for a VPN customer. As we have always been talking about a head office talking to a branch office, but what if they want to connect to the internet? Now the picture here in the slide demonstrates how that can be achieved, wherein you can configure static routes pointing to the customer prefix with an interface on the edge routers. So if we take the Indian bank, the left bottom, right? So he sends a packet to the edge router. He is told, okay, connect to the internet routing table, which is connected off of New York, and that's the way the customer's sites can access the internet. And on the way back, there can be unique static routes for each one of the customer sites. So that is the only thing that the service provider need to be careful about. That means there has to be a unique static route to each of the customer sites. So that way, you can see that the end-to-end connectivity through routing can be built so that the customers can access the internet. Now, continuing on the topic of IPVPNs, there are many situations wherein MPLS is not deployed in some of the service provider networks. This could be in some third world countries or in situations wherein they don't have the expertise of MPLS. So then we talk of this IPVPN